Yeah, Abhishek, is the slide visible?
Yes, sir.
Attend ಮಾಡ್ತಿದ್ದೀರಾ class regular ಆಗಿ?
Yes, sir.
Yeah. Dinesh Kumar, are you there? Dinesh Kumar, Sai Suchit,
Yes, sir.
are you there?
Yes, sir.
So in the WhatsApp group, if you have seen, they have sent one
Yes, sir.
circular regarding the examination. So the examination will be offline. Your final examination will be offline. So you should be more serious regarding the lecture videos. Okay. So be attentive in attending the lecture videos. The examination will be offline. So but the EA may be online. So interview assessment, so test may be online. So we're not sure. Yet is not been decided. So but your final examination will be offline. Okay, so for that reason, you should be more cautious. Is it okay?
Yes,
Hello?
sir.
Yeah,
Yes, sir.
fine. So 7 participants have logged in. Yeah, we're running out of time. Let me start. So in the last class, so the last video, we were discussing regarding so what is a process and abstract view of its execution. So how the process will be dealt in the operating system. So we have a simple program, so by name P, so where we are opening the file so as to do some operation on the file. Okay, so whether we do read operation or write operation, I need to first open the file. So we have a command, so by name open, so as to read the file, so by name info, and the command is a read command. And also, like we're reading the content of the file, as well as I can supposed to print the contents of the file. So this particular program P will be handled by the operating system. So where the address space of program will be having the instructions and the data area and the stack of the process, and the stack of the program P. So to understand these word data area, instructions, and stack of the program P, so we have the upcoming slides where we'll be dealing with the example. So where the stack will be coming into picture. Okay. So yeah. So like in today's video, like we'll be having a discussion on the process states. Of course, we have the detailed explanation of the process states in the upcoming slides. So, but to have a small introduction, let me discuss with the process states. And so regarding module 2, this can be a very important question. Okay, so we have so basically new state and ready state, running state, wait state, and termination state of the process, and the last state may be suspended ready. So regarding the termination state of a process, again we can have the termination of a process. Any process can be ended, any process can be terminated based upon these 4 conditions. So first condition of the termination of a process is self-termination. And second one is termination by the parent process. Again, we have some concept of the parent process and the child process. Again, no need to worry. Like all these will be dealt in the upcoming slides. So, but here we are just naming the different states of the process in which any process can be staying. So we have the new state of a process, ready state, running state, wait state, termination state, and suspended ready state of a process. And I again told that, so this termination of a process can be based upon any one of these conditions. First condition is self-termination. Second condition is termination by a parent process. Third condition on which any process can terminate, can end, is exceeding the resource utilization. So this R is the shortcut what I'm using for resource. Okay, so exceeding the resource utilization. And fourth condition is abnormal condition during the operation. So based upon these 4 conditions, okay, any process can go into termination state. And sixth state is suspended ready. So now dealing with each and every state of a process in short. Okay, So for this, you can assume this particular diagram. So what I have shown here, like here we have CPU, and here we have the main memory, and here we have secondary memory. So the secondary memory can be your hard disk. Okay, so like this can be acting as your like example for secondary memory can be your hard disk, and we have here the RAM. So RAM is also called as the main memory, and here we have CPU. Okay, so the CPU is aware of only the existence of the main memory. Okay, so if any program is staying in the main memory or the RAM here, means that particular process can be executed on the CPU. Means the CPU can only recognize or sense the RAM and not the hard disk or secondary memory. Okay, so regarding this new state of a process, okay, a program which is going to be picked up by the operating system into the main memory or RAM, primary memory, is the new state of a process. So for example, here I've taken a simple process P1 is there, and this particular process P1 is in the secondary memory. So this particular process, I mean, so called program. So why I'm calling it as program and not a process, because still this program or this piece of code is still residing in the secondary memory or the hard disk. Hence, it is not yet been made executable. Hence, this is still a program. Okay, and for this process, and for this program to be executed, right, I need to bring this program from secondary memory. Okay, so from secondary memory, this program needs to be brought into the main program, main memory. So once I bring this so-called program P1 from secondary memory or hard disk to the main memory, so then this can be called as the process. Okay, and this process P1 is in its new state. Okay, so like in simple sense, new state of a process can be defined as a program which is going to be picked up by the operating system into the main memory from the secondary memory. So once any program is coming or being brought from secondary memory or hard disk to the main memory, so then that particular process will be in its new state. Okay, second state is ready state. So after the new state, the next state will be the ready state of a process, where ready state is nothing but whenever a process is created, it directly enters into a ready state. So upon the creation of a process, again the word creation of a process means the OS is aware that this particular process is existing. Okay, so whenever a process is created, it will directly enter into ready state, in which the process will be waiting for a CPU. Means yet the process is not getting the CPU. Okay, so the particular process is not been allotted the CPU. Hence, the process is still in the ready state. Okay, like in which the process will be waiting for a CPU. Means the process which are ready for the execution and the process which are residing in the main memory are called as ready state of a process. Again, we have the same figure being drawn. Again, we have CPU, and here is the main memory or the RAM, and S.M stands for secondary memory. An example for secondary memory is hard disk. Like in the secondary memory or in the hard disk, I can expect n number of programs to be residing. Okay, and among these P1, P2, and P3 and P4 programs, here I am able to bring P1 process, P2 process, and P3 process. So all these process P1, P2, and P3 are in the ready queue. Okay, right? All the process P1, P2, P3 are residing in the ready state. Okay, all these processes are ready. Okay, why? Because like these processes are not being given the CPU for their execution. Means at any instant of time, CPU can execute only one particular program. It's either P1 or P2 or P3. Neither of these processes are being given the CPU for execution. Hence, all the processes are in ready state. And so for this process to be in ready state, all the process P1, P2, P3 needs to be residing in the main memory. Okay, suppose if say like these processes are residing in the secondary memory, so then I cannot call these processes to be staying in the ready state. So for any process to be in the ready state, okay, so what we expect is those processes should be there residing in the main memory, primary memory, or also called as RAM, okay, read access memory. So next is the running state. Okay, so after the ready state, so next state is running state. Okay, here one of the process from the ready state will be chosen by the operating system depending upon the scheduling algorithms. Again, we have so various types of scheduling algorithms where I can schedule any one of these processes which are there in the main memory or in the RAM, and that one single process will be given for CPU to execute. Okay, so here in the running state, the concept is one of the processes from a bunch of processes from the ready state will be chosen by the operating system depending upon the scheduling algorithms. So the process that is accessing the CPU, that process is in the ready state. So what this means is I can expect n number of processes to be present in the main memory. And among these bunch of processes, okay, so based upon the priority and the scheduling algorithms used, I can select any one process among the bunch of processes, and that particular process, say for example, since P1 can be given for the CPU to execute. Hence, now this process P1 is under execution, or now the process P1 is in the running state, we say. Okay, so you can take the help of say these diagrams so as to better understand the concept. Okay, like in all the process states, here I have made use of simple diagrams where we have the CPU, and CPU can only access the programs which are present in the main memory or the RAM, and you do have some processes so which are residing in the secondary memory. Example for secondary memory is hard disk. Okay, yeah. So after running state, so next state is waiting state. Okay, so after running state of a process, next state is the wait state or the waiting state of a process. So when a process, yeah, information regarding the waiting state of processes. So when a process waits for certain resource or input and output operations, then the OS moves the process into the wait state. So as the name itself, as the name itself indicates, if any process is waiting for some resource, let's say keyboard, monitor, mouse, input and output devices, or CPU time, etc. So if any process is waiting for some resource, so then the OS, what it will do, OS will move that particular resource to the wait state and assigns the CPU to the another process. Why? Because the CPU cannot wait for the process which is waiting for some resource. Okay, simply we'll be wasting the valuable resource called CPU time. Hence, what CPU will do is, so what OS will do is, CPU is assigned to the other process which have got all the resources for its execution. Hence, if any process is waiting for some resource or some IO operation, so then the OS will move that particular process to the waiting state. Okay, like according to this particular figure, like here we have so one P1 process was rightly executed by CPU, and if now the P1 process is requesting for some resource, or now the P1 is wanting some resource to resource for execution, so then what OS will do is the currently executing P1 process will be moved to the waiting state, and the OS will also allocate CPU to one more process called as P2. So the second process P2 will be given the CPU for execution. Why? Because the presently executing process P1 is requesting for some resource. So hence the P1 process is moved to the waiting state, and a new process, let's say P2 process, is been allotted the CPU. Okay, so here P1 was accessing the CPU, like here it is, and now it is currently requesting for some resource. So for that reason, the currently executing process P1 is moved to the waiting state, and a new process P2 is been allotted the CPU. Yeah. So the next stage is termination state of a process. So when a process finishes its execution, it comes into the termination state. Say, for example, like in this, suppose if the P1 process has finished its execution, so then that is P1 process can be terminated. So if any process is able to finish its execution, so then the process will be entering into the termination state. And along with, apart from this condition, we do have here, say, 4 different conditions upon which any process can go into termination state. Okay, like as I said, I'll be dealing with individual conditions upon which any process can move to termination individually, like in the upcoming slides. And these are all just for your better understanding by taking the help of some diagrams, okay, where we are dealing with the process states, where we have here normally 6 states will be there for any process, okay, where we have the new state, ready state, running state, wait state, termination state, and the last one is suspended ready state. So now we'll see this suspended ready state. Okay, so for this again, like I'm taking the same figure, like where we have CPU and we have the main memory or the RAM, and we have the secondary memory. Example for secondary memory is a hard disk. Okay, so regarding suspended ready state, a process in the ready state which is moved to the secondary memory from the main memory due to the lack of resources. Okay, such process will be there in the ready state. So according to the figure, like in the secondary memory or in the hard disk, you can expect a number of processes to be residing. And in the main memory, like we have here P1 process, P2 process, P3 process. So here P1, P2 are in the ready state. So, but now they want some resource. So say, so this process P1 is in need of, say, printer, and second process is in need of any other resource as such. So here, so both these process P1 and P2 are requesting for some resource. Hence, that there is no use of keeping these 2 processes in the main memory. Okay, why? Because as these 2 processes are willing to use some resource, or like these processes are requesting for some IO operation, hence there is no fun in keeping these 2 processes in main memory. So for that, what I can do is I can move this P1 and P2 to the secondary memory or the hard disk. Okay, so here both the resources are busy, so no fun in keeping the P1 and P2 in the main memory. So I can move them from this main memory to the hard disk. Okay, yeah, so now this so-called P1 and P2 will be in which state? Suspended state. Why? Because these 2 processes will be temporarily suspended as they are requesting for some resource or some IO operations. Hence, I can suspend these 2 processes by moving them from main memory to the secondary memory. Again, so when these resources P1 and P2 will be getting some resources, what they need, I can take back this process from the main memory, right? So from the hard disk. Okay, like it says, process was in ready state earlier and it went to suspended state. Why? Because those processes are having some shortage of resources. So due to the lack of resources, the processes which are in the ready state, okay, so the processes which are in the main memory were suspended. Okay, why? Because they were in need of some resources, or due to the lack of resources, we have just suspended those processes, right? Hence, now they are residing in the secondary memory or in the hard disk. Okay, yeah. So the 7th state is after suspended ready. 7th state is the suspended wait. Okay, suppose if the process is in the wait state, okay, and it is requiring a resource, okay, and if there is lack of resource, so whatever the resource that the process is requesting, that particular resource is not available, right? Okay, like in that case, the OS will remove that process and put it in the secondary memory. Okay, suppose if the process is in the waiting state, like earlier what we saw was suspended ready, where the processes were in the ready state. So but in the suspended wait, now the processes are in the waiting state. Why? Because they are requesting for some resource and we have currently the lack of resource. So we have a shortage of resource. So then what OS will does is, So what OS will do is OS will remove that process and put it in the secondary memory or the hard disk. So these processes complete their execution once the main memory gets available and their wait is finished. Okay, yeah. So the process is already in the wait state. Okay, hence we call this as the suspended wait. It means the process are already in the wait state. Why? Because they are waiting for some resource. They move this from main memory to the hard disk. Hence, they are being moved from main memory to the hard disk. That is, the process are made to wait in the hard disk, okay, rather than in the main memory. So when the resources are made available to the processes, then they can be again moved from the hard disk to the main memory. Okay, so in short, you can understand the meaning of the different states of a process where we have dealt along with easy understandable figures, like we have seen the new state of a process and ready state, as well as running state, wait state, and termination state, and suspended ready state, as well as suspended wait state of a process. Okay, I again repeat, all these are just the basic information what you need to have before we proceed. Okay, so for this, I thought of using some figures, and these figures are taken from the net. Okay, so from the Google, like I've taken these figures for easy understanding. Okay, yeah, right. So the OS will allocate unique identification number to the processes so as to know the termination of the process. So the OS will be having an idea. So whether, say, this particular process P1 is in ready state or in like in whatever state the process is. So the information regarding the existence and the state of process and the information regarding the process is known to the OS using the unique identification number, which is being allotted to all the processes by the operating system. So once the process is running on CPU, so then OS will be able to allocate resources to it. Okay, so if the process is in the running state only, so then the process will be in need of resources. Suppose if the process is in the secondary a secondary memory or in the hard disk, so then such processes which are staying in the secondary memory or in the hard disk will not be able to consume or take or receive any resources. Okay, so any process which is there in the hard disk will not be in need of any resources. Suppose if the process is in the running on the CPU, right? Like in that case, any process will be in need of the resources, and OS will be able to allocate the resources based upon the availability. Okay, so sufficient memory to accommodate address space of the program, like this can be the resource, so what a process needs. And other example is IO devices to interact with the users, etc. Okay, so once any process is running on CPU, so then that particular process is able to have the request for resources, and OS responsibility is to allocate those resources to the process for its complete execution. Okay, so next, according to syllabus now, so we have here so 6 different components of a process. Like as I told, you need to concentrate on the heading as well. Why? Because like in the examination, all the questions will be using these predefined headings as per the book. Okay, like in that regard, the next concept is different components of a process. So basically, we have 6 components of a process, and those are identification number, okay, ID number, a unique ID number. Second one is code. Third one is data. Fourth one is stack. Again, we have the example to explain the stack better. So this stack will be coming into picture if the code of the program is using some function calls or procedure calls. And fifth component of process is the resources. So we have the various types of resource like CPU time, memory, like M for memory, I/O for IO devices, and this is network throughput, electrical power, etc. So we have CPU states, okay, like as we have this PSW. So this PSW stands for processor status word, and GPR stands for general purpose registers of CPU. So we can have the indication of various states of the process. okay, like using this PSW and the general purpose registers of CPU. So here, like basically, we have six components of the process, and from examination point of view, you need to remember all these six components of the process. Okay, like starting with this ID. Like we know that ID is given by the operating system so as to know which process to execute next. Okay, so which process is over and which process I need to execute next and how to identify the process. All these information will be known to the operating system if and only if the process is being given an ID. Okay, so like this is the unique ID that is being assigned by the operating system to the code or to the program or to any process. Okay, like it is a unique number given by the operating system to any process or any program. So with the help of this particular ID itself, any operating system will be able to identify so what all process is to be executed next, and once the process completes execution, so then OS will come to know so which process execution is over, and it will try to access the next process. So the CPU will be given to the next process for execution, right? Yeah, second one is uh, the code. Okay, so the second component of process is the code. So this code is nothing but the the program, okay, or the process or the programs, so what any user will be able to write. Okay, and third one is the data. So this data is used in the execution of the program, right? Input data from user, like example for this data can be the input data, input information that is being given from the user via the keyboard, or the data can be also coming from the database. So like it is the data used in the execution of a program, including the data from the files. Okay, that is the data which is inputted for the process. Like it might be coming from the inbuilt database, or in real-time applications, any user can enter the data via the keyboard as well. Okay, that is input what is fed to the program or to the process for its successful execution is the data of the process. Okay, and next one is the stack. So to explain this particular stack, like here I've taken a simple example. Okay, so like so this stack is there, and this stack is coming into picture when any program, any process is using the function calls or the procedure calls. Like these functions are the subprograms, and like the subprograms in the high level languages are called as functions, and the same subprograms in the assembly level language programming, like we call it as procedures. Okay, so these contains I mean uh, the stack so this stack contains parameters of the functions and the procedures called during the execution of a process or program, and the return address as well. Like I said, so the stack will be coming into picture if the code is involving the function calls and the procedure calls. Okay, so to explain this, like I've taken a simple example where I'm adding two numbers, where A and B are the two numbers to be added. Okay, so for that I can write down the main program here. So we can have the main, and we have like declared A and B are of type integer, and a function call made is the sum. Okay, like in the main program, here I'm not adding A and B datas. Here I'm not adding A and B datas in the main program itself. Okay, so for that, what I can do is I can take the help of a function called sum. Okay, like where this sum is the subprogram. Okay, and this subprogram's main function is to add A and B datas. Okay, so to this sum, we'll pass two parameters x and y. Like as you can see here, in the subprograms by name sum, here I've declared x and y. Okay, and this summation of x and y are been assigned to the z, and this z is returned to the main program. Okay, yeah, like as you can see here, like in the main program, here I have in the main program, I cannot be adding the two numbers A and B directly. Okay, A and B data have not been added directly. So what we do is I will read the two I will read the, say, two integers a and b, and I will call a function sum, right? And the values and the values of a and b are being passed. So when I call the function sum, where this a is assigned to, so this a is assigned to x, and this b is assigned to the y, and the z is being calculated using the values of x and y, and the same z is returned back to the sum. Okay, so this is the calling program where like in the main program, like I'm calling the subprogram called a sum, and this is the called program sub by name sum. Okay, right. Like in such cases, the stack will be coming into picture. Means whenever the control of execution is being jumping from the main program to the sub program, the address of next instruction. So for example, the address of next instruction, I mean, like the next instruction is this printf. Okay, so the address of the next instruction, say the printf instruction address. Okay, its address needs to be stored somewhere. So this temporary memory where we are storing the address of printf or the address of next instruction after sum is called as the stack. Okay, so once the execution of subprogram is over, so then what we do, then the control will be able to return back to the main program by retrieving the address that was stored in the stack. Okay, and it can jump to the particular address where the next instruction after sum, that is the printf is been written. Okay, right. So you can explain this stack where we are storing the address of next instruction, and this stack is coming into picture when our program is using some function calls or the procedure calls. So to explain this, you can take the help of these two programs, where in the main program, I'll be calling the subprogram or the function, say by name sum. Okay, and we can have the mapping of a and b integer values to x and y, where we can have the calculation of x plus y, and I can calculate the z, and this z is being returned to the main program. Okay, hence no need to perform the addition of a and b in the main program. So for that, I can write down one more program where I can call the subprogram in the main program. Okay, right. So the sixth state is so next component of the process is the CPU state, and this CPU state, like, we'll be having the use of the processor status word, so-called PSW, and general purpose registers of CPU will be coming into picture. So now let us see this so-called the next component of process, CPU state. So the CPU state can be explained like using this. So the CPU state is composed of the contents of the processor status word, and so-called PSW, and the general purpose registers of CPU. So these words, PSW, process status word, and the word general purpose registers of CPU are more common in microcontrollers or in microprocessors. So like in case of any microcontroller like 8051 or any microprocessor like 8086, 8085, etc., we have different registers like process status word, whose main function is to tell the status of the particular program. Okay, so these PSWs are nothing but some set of registers which are usually 16-bit in length, and they are able to indicate the status of the program. So for example, like when we add any two numbers, so then like whether we are having a carry or we're having the auxiliary carry to be generated, or if we have the answer as 0, okay, like using the different flags, okay, in the 16-bit register, you can have the information regarding the status of the operation what we are doing. Okay, so for example is, upon adding any two numbers, okay, so what kind of result is obtained, and whether we have a carry, so whether the answer is 0 or a non-zero result is obtained. So such information will be obtained using the processor status word, whose main function is to indicate the status of the program. Okay, and regarding this general purpose registers, so these are nothing but the small registers or small memory devices which will highlight the CPU state. Okay, so these GPS are very much less in number and small in size, and their usual size will be of 1 byte to 4 bytes, and these are the fast memory devices. So we can have the better understanding of the status of the program using this process status word as well as the use of general purpose register, and these 2 points can be explained in the CPU state. Okay, yeah. So till now, what we have seen is regarding the different components of the process. And I think this is a very much important question in module 2, explain the different components of the process. And according to your syllabus, you have so 6 different components of process. Those are like unique identification number for each and every process that has been assigned by the operating system to all the process. Okay, second one is the code, third one is the data, fourth one the stack, and fifth one the resources. Like I said, you have so many resources of the computer system, and upon the request raised by any process for any resource, the operating system can consult the resource table and get the information regarding the free or availability of the resource, and the operating system can assign the resource to the requesting process. An example for those resources can be the CPU time, so then memory, input and output devices, network throughput, etc. And the last component of the process is the CPU state, where we have the use of the process status word and the general purpose registers of the CPU. Okay, so you can explain these concepts along with this six components of a process. Okay. So next is relation between the process and the programs, and this I'll be taking this in the next video, not a problem. Yeah, so regarding participants, is this is this okay? You need to glance all the information. You need to glance all the information without fail. So you can log out. Okay, so you can log out now, and again repeat, don't forget to let's analyze the slides and keep on reading this. Okay, yeah, thank you.